Have you ever wondered why pi is so celebrated? Have you ever wondered why people care so much about pi being irrational or transcendental? Well, today on Pi Day, I'm going to explain Pi's story to you in the next 20 minutes.
Now, in Euclidean geometry, two figures are said to be similar if one of them is a zoomed out version of the other. In other words, if you can take one of those figures, scale it, and place it on top of the other. This means that any two side lengths or any kind of lengths of these two figures are proportional to each other. Now, since any two circles are quite clearly similar, this would mean that if you take two of its lengths, say a circumference and the diameter, the ratio of these two should be constant. Okay, so this constant is generally called pi. Now, did you know that although this ratio was studied in various civilizations at various times by various people, the name pi, the Greek letter pi, was attached to this ratio very, very recently. In fact, it was named just around 300 years ago. Right? However, it was studied quite widely. Any circular object, you can measure the circumference and measure the diameter. I'm going to do it right now with a red stool. Alright, so here's a red stool, and I'm going to measure its circumference, its diameter, and here's the ratio. Measuring is different from computing. Measuring the value of pi is a scientific process. You take a real life object, you measure the circumference, you measure the diameter, and you take a ratio. By computing, I mean you don't really measure it, but rather you calculate it from the laws of Euclidean geometry. So, chapter 1 is computing the value of pi. And there is a long history to this story. We start in the ancient world. Around 2000 BCE, Egyptians, Babylonians, Sumerians had already computed the value. So, what was their best estimate of pi? Their best estimate was up to 1 decimal place. Not bad at all for 4000 years ago. Next, we come to 250 BCE. The Greek genius Archimedes computes the value of pi up to 2 decimal places. In fact, this is the first time he just doesn't compute it, even tells you how he computes it. Because he explained how he did it, this was actually used later by other mathematicians to fine tune and compute pi to a better degree of accuracy. 400 years later, Ptolemy calculated the value of pi to an additional degree of accuracy, 3.141. But really, the highlight goes to Zhu Chongzi from China. In 480 CE, he actually computed the value of pi up to 7 decimal places using the same method as that of Archimedes. So this method is called the Archimedes circle cutting method. It's generally called the circle cutting method. And the idea is really simple. What you do is you approximate a circle by an inner polygon, regular polygon, and an outer regular polygon. In other words, you inscribe a regular polygon inside the circle with a large number of sides. You can see that these polygons approximate the circle from inside. Secondly, if you start inscribing a circle within a regular polygon, you will see that it will approximate the circle from the outside. Archimedes' genius lies in the following. He did this for regular polygons of sizes hexagons, that is 6-sided. Then he did it for 12-sided by cutting the arcs into halves. And then further, he kept cutting the arcs into halves by then constructing it for 24, then 48, and 96, and then he stopped. So Archimedes' insight lies in the fact that one can calculate using methods and laws of Euclidean geometry the exact value of pi by looking at polygons of the form 3 into 2 power n. In India, around 500 CE, Aryabhata also gave an approximation of pi. You take a circle with diameter 20,000, its circumference is 4 plus 100 into 8 plus 62,000. Okay, so 62,832 by 20,000, 3.141 and something else. Really, in other words, Aryabhata was actually accurate up to 3 decimal. I would be very interested to know what methods Aryabhata used to calculate this particular formula. Alright, so let's move on into computing pi using powerful methods like calculus. Now let's look at 1400 CE. So we have Madhava of Sangamagrama from the Kerala School of Mathematics who computed the value of pi up to 10 decimal places. Now how did he do that? He's also credited with the series formula for pi by 4. So let's look at that. Here, as you can see, pi by 4 can be written as sum of reciprocals of odd numbers with alternating positive and negative signs. Okay. Now look at this. This is an infinite series. It goes on and on forever. What it what this equation really means is that you can compute pi to arbitrary degree of accuracy. Now, this series was discovered 200 years later as well in the calculus era in the Europe, and it's also often called the Leibniz series or the Gregory series. And now, one thing to note is that I doubt whether Madhava actually computed, the value of pi up to 10 decimal places using this series, because this series is known to be notoriously slow. Not that this series is a special case of the power series for tan inverse x. In 1600s in Europe, when people were computing the values of pi to arbitrary degree of accuracies, um, people came up with better power series that could be used to compute the value of pi.
In this context, we would be amiss if we do not mention John Machin, who in 1706 computed the value of pi to 100 decimal place. Yeah, that's right. He did this by actually rewriting the pi by 4 formula in terms of tan inverse. He basically again used the Madhava series, but this time it's much more faster because of the tan inverse 1 by 239 term. At this point, you might be wondering though that people have computed the value of pi up to 100 decimal place, but none of us even remember it up to 10 decimal place. So there is a really nice mnemonic that I want to present to you. Mnemonic reads, I want a drink delicious of course after a heavy chapter involving quantum mechanics. If you look at the words, number of letters in the words, then you can actually get the value of pi. It's 3.141592653589979. At this point, you must be wondering whether these computations will ever end. Already people have computed things up to 100 decimal places, and will we have to keep computing forever? Well, this question was asked also by many mathematicians. To understand this, let's go to the notion of a decimal representation. Writing in decimal representation means writing in terms of powers of 10. Let's consider an example. Suppose you write the number 1 by 7 in decimal expansion. You will see that it will be of the form 0.142857 repeating. Okay, what does this really mean? 1 by 7 is essentially 1 by 10 plus 4 by 100 plus 2 by 1000 and so on. So it's written in terms of powers of 10. Now let us consider writing it in some other base. Look at 1 by 7 for instance. If you write it in base 7, it will look like 0.1, just like 1 by 10 is 0.1 in base 10. Let's try to write some other numbers as well. If you write the number 4 by 9, then it will be 0.4 in base 9. This leads to a very interesting observation. Whenever you have a number which is a ratio of two integers, if you write it in the base of the denominator, then you will have a finite expansion. In fact, the converse is also true. If you have a finite expansion, when you write it in terms of powers of 1 by b, if there are only finitely many terms, then it is, when you take common denominator and rewrite it, you will see that it is basically a ratio of two integers. Now let's apply this observation to pi. Is there a base in which the expansion of pi stops in finite steps? If you think about it, this question reduces to the question whether you can write pi as a ratio of two integers. Numbers that can be written as a ratio of two integers are called rational numbers. Okay. So Euler, in his book The Analysis of the Infinite, Introduction to the Analysis of the Infinite, asked the following question. He wondered whether pi is not rational. Okay, and this was in 1748. Sure enough, within a few years, in 1761, Lambert proved Euler's suspicion. He showed that pi is indeed not rational. If you are interested in a proof of this fact, you can look at Carl Siegel's book on transcendental numbers, where he proves this within page 9. He of course uses the irrationality of E to do this, and I encourage all people who are interested to look at this book. So now pi is irrational, but we already know lots of irrational numbers, right? We know root 2, cube root of 3, maybe 100th root of 2024. Any mth root of n where n is not a perfect n power is in fact irrational, and often the sums and products of these numbers are also irrational. So a natural question arises. Maybe pi cannot be written as a ratio of two integers. It's fine. We know now that pi cannot be written as a ratio of two integers. But maybe you can write pi as the sum of ratios of some irrational numbers that's well known of the form mth root of n. Okay, generally called radicals. So, is that possible? Well, historically, there are lots of such algebraic approximations. The most famous ones of these started from root 10 or root 2 plus root 3 and many others. Root 10 in fact goes back to Brahmagupta, and the last two, as you can see on the screen, are due to Ramanujan. My favorite one is basically the last one. You'd be surprised to know that this Ramanujan formula is actually accurate up to 18 decimal places. Insane. So, if you think about it, now you might start feeling that, wait a minute, maybe there is some super Ramanujan formula where pi can be accurately be written as, sum of reciprocals and ratios of these radicals. Radicals are of the numbers of the form mth root of n. Now, that question naturally arises. Now, let's think about what properties these radicals have. Now, for instance, if you take square root of 2, it satisfies the equation x square minus 2 equal to 0. Square root of 2 plus square root of 3 satisfies the given equation there equal to 0. And it turns out in general, the sums and products of these radicals and their reciprocals will always satisfy an equation which is made out of powers of x and integers. More precisely, if something is written as sums of products of powers of x and integers. These kind of expressions are called polynomials with integer coefficients. Now, a number which satisfies a polynomial with integer coefficients, an equation involving polynomials with integer coefficients, is generally called an algebraic number. So the natural question now is whether pi is an algebraic number. As usual, Euler suspects that pi is not algebraic in 1775. Well, is it? It turns out we'll have to wait another 100 years to figure out that it's actually not algebraic. In 1882, Lindemann proves that pi is not algebraic. You can read a proof of this in Carl Sagan's book, and he proves this within the first 23 pages. In fact, he proves the more general version called the Lindemann-Weierstrass theorem. If you are a motivated undergraduate or a graduate, you can look at this proof. Now we come to a surprising way of measuring pi. Note, measuring, not computing. Okay? So we have to go back all the way to the 18th century where Buffon proposes the following question. And the question is, suppose you take a floor made of parallel strips of wood, each of the same width t, and you have a needle whose size is less than the thickness or the width of the parallel strips. Now, if you throw a needle onto the floor, what is the probability that the needle will cross a line? Well, Buffon computed the probability, and it turns out the answer was 2L by pi t. The probability calculation has a pi in the denominator. We can then calculate the value of pi empirically by doing this experiment. I'm so excited about this. I did this experiment at home and all the people in my family participated with this experiment. So what did we do? I just took a A4 sheet and drew parallel lines, took a matchstick which is the same width as the distance between the lines, and I performed the experiment. The formula to calculate is simple. Calculate the probability, take the reciprocal and multiply by 2. So let's start the experiment. Now, the whole family participated in the experiment and we made 4 sets of 10th rows of 13 matchsticks each. Here is a table of all possible outcomes. If you now calculate the total probability, it is 310 by 520. Now if you reciprocal this and multiply by 2 to get the value of pi, you get the value of pi to be approximately 3.35. The Buffon's needle experiment is known to be a lousy way to compute the value of pi. We'll see more about this lousy story in the next chapter, which is pi drama. You might have heard of K drama, Korean dramas, and J dramas, but here's some drama relating to the number pi in its 4,000-year history. Now, the first story that we're going to discuss is a little sad. The setting is World War II. Edmund Landau was dismissed from Göttingen University, and his dismissal was defended by the Nazi mathematician Bieberbach, who said that he gave a racist definition of pi. He called Landau's definition un-German or un-Aryan. In fact, the definition was really pretty standard. It was basically the definition that pi by 2 is that number between 1 and 2 whose cosine is 0. Okay, which is a pretty harmless looking definition if you ask me. Well, the next drama is not really a drama, but it's a little bit of history about the Pi Day. Pi Day really started in America and was started by Larry Shaw, who started this tradition about eating pie on Pi Day. Now, in America, they follow the format MMDD, because of which 314 will look like pi. But actually, most countries in the world follow the other format, DDMM. We can celebrate Pi Day on 22nd July. However, there's really a funny drama that America has given us. First of all, on February 6, 1897, Indiana proposed a bill to declare pi is equal to 3.2. The more funny thing is that it passed unanimously, and further, the person who proposed it, Mr. Goodwin, basically said that this formula is copyrighted and that all the other states would have to pay for his wrong formula. The last story is related to the Buffon's needle problem and how terrible its approximations generally tend to be. So in 1901, Mario Lazzarini, Italian mathematician or amateur mathematician, I have no idea, but basically Mario Lazzarini said that he built a machine to perform Buffon's needle experiment, some kind of a washing machine. He further claimed that he computed the value of pi up to 6 decimal places and gave a list. This list looked very suspicious. So much so that many years later, 90 years later, there was an article in the Mathematics magazine explaining how Mario Lazzarini's calculation of 6 up to 7 decimal places was really lucky by Lee Badger. Now, calling Lazzarini's calculation lucky was basically quite a charitable view. It was actually nothing short of suspicious that he could get up to 7 decimal accuracy with just 3,408 throws. In fact, in the same year, Professor Maddox wrote a paper in Nature explaining that Lazzarini is nothing but a bare-faced fraud. Well, his words, not mine. However, there are people who believe that Lazzarini's article was actually a prank, a joke, and should not have been taken seriously. With this, we are at the end of our presentation. So, happy Pi Day, everyone. Bye.